All right. So this is just a little background material about wrangling, why it's important. I covered this in the last lesson, so I won't dwell on this too much. But remember, it's just this general process that begins with a question of where am I going? In other words, what analysis am I trying to do? What plot am I trying to make? And what does my input data look like? And what do I need to do to it to get to where I'm trying to go? So this is all leading you up to this understanding process where you're going to hopefully gain some insight into your data set. So last time we talked about some really simple functions with dplyr, selecting variables, filtering observations, making new variables with mutate, renaming things, arranging things, all sort of your core functions of dplyr that you'll be using all the time if you so choose to use R after this training. So in this lesson, we are going to talk about some other functions available in dplyr and tidyr, which is another package that comes with the tidyverse. So we're going to talk about data joining. So how do you combine two data sets? We're going to talk a little bit about what tidy data are and why you should always try to strive for a tidy data set. And then we're going to talk about how to use summarize data. And that's a really generic term, but there are some pretty nifty tools in dplyr and tidyr to help you synthesize your data in a very quick way. So let's just start off with combining data. There's obviously a lot of reasons why you would want to do this. The two data sets that I provided you with for this workshop, the fisheries data and the station data, are two things we might want to combine because one of them, the station data, has locational information, which we'll use in our mapping session. And in order to look at, say, for example, how fisheries catch changes in space, we want to combine those two data sets because we have the fish data and the locational data. They're two separate things at this point. We want to join them up. And so that's the essence of joining, basically combining two data sets with keys that are shared between the two. So we'll revisit this concept called keys. Actually, we're visiting it now. So keys is fundamental to what you want to do when you're combining data. You need to identify what is that shared attribute that you can use as a key when you're joining two data sets. So I have some examples of what joins look like. And again, this is information from the R for Data Science text that I showed you, I guess, at the beginning of the last lesson. This is a textbook that's online. A lot of the examples I have today are from this book, these graphics in particular, because I think they really demonstrate quite well what a join does. So there's a couple different types of joins. The first one I'm going to show you is an inner join. And so if we conceptualize this, think of these two different data sets here. So this is one data set on the left, and this is another data set on the right. So this first data set has 2 columns, 3 rows. Same thing for the second data set, 2 columns, 3 rows. What an inner join does is links these two data sets by shared keys, where those keys are only shared between these two data sets. So this column here, 1, 2, 3, and this column here, 1, 2, 4, this is our key. So think about in our fisheries data set, our key would be the site name. So I think that's the reference column in the fisheries data set. So we have a site name in our fisheries data, and then we have a site name in our locational data. Those are our keys. Those are the two, or that's the column that is allowing us to combine these data. Now in an inner join, again, we're only combining data sets where the keys are shared between the two. So when we join these two, we're only left with keys 1 and 2 because the first data set had these keys and the second data set had these keys. So 3 is not shared between the two, neither is 4. So we end up only with the keys that are shared between the two. And we're combining the attributes that go along with each key. So in the first data set, we have an x1 value in the x column and a y1 value in the y column, and now they're linked up through that same row with the key. So hopefully that's pretty clear what that means. The second type of join is an outer join, and so this comes in 3 different flavors. So with an outer join, what differentiates that from an inner join is that sometimes you might have keys that are not shared between the two data sets in the final product that you've joined. That's just why it's called an outer join. But an outer join comes in 3 different flavors: a left join, a right join, and a full join. So there's some nuance to what each one of these things mean. And if you don't take anything away from this next description, try to just think about a left join, because that's the one I use most often. Now, what a left join means, or what that does, is essentially we're still joining data sets, obviously, but instead of, as an inner join, only retaining the keys that are shared between the data sets, we're retaining only the keys that are in the left data set and matching those in the right data set that are shared with the left data set. So that's a left join. So here we have keys 1, 2, and 3. Because this is a left join, we're always going to have keys 1, 2, and 3 in the join data set, but only keys in the right data set that are shared with the left data set are joined in the final product. So 1, 2, and 3, here's 1, 2, and 4. So we see 1 and 2 being joined to the left data set here. And then 3, which is a key from the left data set, is retained from the left data set, but there's an NA value, meaning there's nothing there for that one, because that's a key that wasn't found in the right data set. A right join is the opposite. So here we're using these keys as our sort of master list for the right, for the join rather, and we're keeping only keys that are shared, only keys that are in the right data set. So here in the final product, we have keys 1, 2, and 4, and only the rows from the left data set with those keys are included, and then there's an NA there for the key number 4, because that wasn't in the left data set. And then a full join is basically saying, let's combine everything, keep all keys. It doesn't matter which ones are shared between the two. We're going to combine ones where they are shared, but ones that aren't shared between the two data sets, they're still going to be in the final data set. So this is actually kind of a useful one if you want to keep all observations across all data sets. So again, only keys 1 and 2 were shared between the two. 3 was in the left data set, but not the right data set. 4 was in the right data set, but not the left data set. So that's joins in a nutshell. So we're gonna, that's conceptually kind of hard to grasp if you've never seen that before, but doing it in practice is really easy. There's this function called join, and depending on what kind of join you want to do, the name of that join is preceded, or the function is preceded by the name of that join. So left join for left join, right join for right join, so on and so forth. So I'll copy this to the live coding so you guys can have it. By the way, you can separate your script by sections. That's what I've been doing so far in the live coding. There's a shortcut, Control-Shift-R in RStudio, Control-Shift-R, where you can pop up that little dialog there and say, here's my section name, and then it pops that in. What's cool about this is you can collapse bits of code, so it makes readability a little easily. And then you can also see the section names in this navigation pane up here. So that's what I've been using there if you want to use that handy feature. So I've just copied in. You should have imported, you should have this data set already imported from the last lesson, but we'll do it again. Don't forget to always load the libraries that you're using. If you didn't close R in between the lessons, this is not a problem, but you can always reload the library, no problem. But we're going to import fishdat. We get some information there about what it just imported, column names, the type of data in the columns, and then we're going to import the station location data, which is also in that data folder. So we see that one right here. So remember, we have to use the relative file path. So my working directory is right here, desktop, R workshop, and in that we can click that button to go to the home directory for the working directory, and we can see there's the data folder and then the files in there. So run that script. Now it's called station location, or statloc for short. View that. So here's reference. This is the site name, and then here's the latitude and longitude data that corresponds to each site. So this is not an uncommon way for you to work with environmental data. You often have just locational information in separate data set that you'll want to join with actual data. And in this case, our actual data is fishdat. So remember, the first thing about joins is you need to identify your keys. So again, the key is the column that is the shared piece of information between the two data sets. So if I'm looking at the first 6 rows of each, I know that there's catch data for the station and the date, and I know that there's latitude, longitude data for the stations and the station location file. So I need to look at these and say, okay, what's the key name? So here's fishdat, that's reference, because did that wrong. So I'm skipping ahead here. Statloc. There you go. So there's the first 6 rows of statloc, and then there's the stations there, and so the key name is there as well. Sometimes the key is there and shared between the two data sets, but the name might not be the same between the two data sets. So this might be called like station or something like that, but this is called reference. Before you do a join, you have to change the names so they match between the data sets, just as a little piece of advice. Because if you try to do that, if you try to join and the names aren't the same, R will get mad and yell at you. So here's what I'm doing here. So now I know that that's our key. I want to do a left join and use the reference column as my key. We specify the key using by equals. So I'm joining by the reference column. And I'm going to do a left join. So we can run that. Now we have that. Now, what's always good with the join, notice we didn't get any errors, so it worked, but because there's different types of joins, it's always good to check your results, because you might get a different result depending on what type of join you want to do, and you always want to make sure you basically did what your intention was. So let's just look at the dimensions of fishdat. So there's 2,800 rows there. We'll look at the dimensions of statloc. So there's 2,100 rows there. Now, because this is a left join, we're keeping all of the keys in fishdat, whether or not there's a total match in statloc. Conceptually, that's just easy for me to think about, so I use left joins a lot. But in order to check to make sure that we did, or that R did what we wanted it to do, we can look at the dimensions of the joined data set and verify that indeed there's the same number of rows, meaning we kept all of the rows in fishdat and joined the locations to only the rows in fishdat where the keys matched. So this little verification that there's 2,800 rows in FishDat and 2,800 rows in the join data set tells me that this is done correctly because we didn't lose any information in FishDat by that left join. Hopefully that made sense. But you can always look at it. So here's our join data set. Should look exactly the same as FishDat, but now we have these two new columns, latitude and longitude, that are appended to the end, because this was coming from our StatLoc data set using the reference column. And we only have one reference column because it basically just synced those two up and matched the rows to the rows where they were the same. So hopefully that makes sense to you. Yeah, we're going to do that. So this is a couple steps here that are a little more involved. So we're going to use some other functions from the last exercise to remove some columns or get some columns first, filtered by a gear type, and then use a full join. And then when you've done that full join, I want you to look at the resulting data set and tell me if it looks any different than if we were going to do a left join. And as always, you can cheat there, but you know, try not to do that. So I'll put 5 minutes on the clock and then we'll talk about this exercise. So just a heads up about item 4 in exercise 6, just ignore that. That's just me not updating examples correctly. So when you do join the data set, just check the dimensions, number of rows, ignore the rest. All right, gang, hopefully that wasn't too challenging. I wanted to add a couple extra steps in there because the join is almost trivial once you understand what it's doing. But let's just briefly walk through the steps, and then I want to explain why I wanted you to look at the dimensions of the final data set when you were done. Because there's important things to note about checking your results with joins, as I attempted to describe earlier. So I'm going to use pipes. Hopefully you guys are getting comfortable with that. Fishstat, Control-Shift-M, select reference, using tab completion, sampling date, gear, and then common snook, pipe again. I also should have mentioned earlier, it's convention to start on a new line after you do a pipe. You could totally do it like that, but one of the whole objectives of pipes is to help with readability. So if I'm reading this from left to right, top to bottom, if I have this on the same line, it's not quite as simple to read. So do it for yourself and do it for others that are reading your script. Okay, then we're going to filter by gear equals 20, type again, and then it's up to you whether you want to have this to be part of the pipe, but my preference is to keep it in the pipe because this is sort of one workflow for wrangling. So all you would have to do here is put in stat-loc and then specify the key. If you weren't doing this with the pipe, you could call this whatever, and then back up. You'd have to put in the output from this set of pipes into the first argument for this one, but we're not going to do that. So we're just going to do it all in a pipe because pipes are awesome. So that's what that looks like. And I'm going to cross my fingers that I've done it right. There we go. And then we can look at the first 6 rows. So just for sake of argument, let's just look at the dimensions of this, or just the number of rows with the nrow function. I'm actually going to try to keep up with that, put that in the script there. So this has 2,200 rows. We can look at the dimensions of the original and then dimensions of stat-loc. So what we did was essentially, we have less rows in Fishstat. We did a full join. So what happened? Well, because we filtered by gear equals 20, we're already removing rows in Fishstat. So we can, I'm actually going to go back to this and do this on a separate line. So I can better show the difference to you. We'll run that. So EX6, 955 rows. So by removing everything but gear type equals 20, there's 955 observations. Now when we do the full join, again, stat-loc, station locations, has 2,173 observations. We're saying keep all of the keys, no matter which ones are shared between the 2 data sets. So that's why when we look at the number of rows in join EX6, we have a lot more than we had in EX6 for one, so this first guy, and then we have more that were in StatLoc because there were probably some keys in EX, definitely there were keys in EX that weren't in StatLoc, and then there are keys in StatLoc that weren't in EX6. So when you do a full join, it's not uncommon to have as many or more keys or number of rows in the final data set in the join data set. So just to show you, if that wasn't clear, what that is. So here's the join data set. I'm going to sort, let's see, find some examples. So here's a good example all the way at the end. These are instances, these rows here are instances when there was something in StatLoc, because we have locations, but nothing in our gear or in our filtered fisheries data set. So because it's a full join, we're keeping everything. Trying to find ones where it's the converse of that, but you'll just have to take my word for that. So that's a full join. Hopefully that was clear. So let's move on to the next set of instructions or part of the lesson. All right, so let's talk a little bit about tidy data. As you might imagine, this is a really important concept. The entire tidyverse is built around this idea, which is why it was named after this. Tidy data, as I mentioned in the beginning, are important because it establishes a set of rules for how data could be set up. And if you follow these rules, it will make your life a lot easier in terms of understanding how a data set is structured so you can do analysis down the line. So these, again, are examples from the text R for data science. And what this is showing you are 4 different tables where each one shows data from the same original data set, but set up in different ways. And only one of these data sets is tidy. So I'm going to go through this and you can maybe guess or try to figure out which one is tidy. But I want to show you these 4 examples because they're really good to demonstrate how people might store data in ways that aren't tidy and what you can do about it. So here's table 1. What this is showing you, this is an old data set, but I think it's kind of timely, showing number of cases of something, some ailment per population in a given year. So we have 4 columns, one for country, one for year, number of cases in that country corresponding to a year, and then the total population for that country. Here's table 2, showing the same thing, but now we have a new column called type, where it specifies whether this value in count corresponds to a case, number of cases, or the population. So this is kind of like converting the first data set into long format. And then we have table 3, which is the same as table 1, but now we have a rate column, which is showing us the cases divided by population. And then we have table 4, which is set up in 2 parts now. We have 4A and 4B, where we have 4A is showing us just the cases by year, so 1 column per year, and then table 4B is the same, but it's the country population with the population at a year in each column. So if I was doing this in person, I'd ask people to shout out their answer for which one is tidy, but the answer to that is only the first data set is tidy. Intuitively, this makes sense, but there's a couple specific rules that make this a tidy data set, and these rules are right here. So there's 3 of them. Each variable must have its own column. That's the first rule. Second one is each observation must have its own row. And the third rule is each value must have its own cell. Graphically, that's what this looks like down here. But you can look at these examples and I could tell you why this isn't tidy. So table 3 is the easiest one. There are 2 values here in the same cell. So this is not tidy. That's a terrible way to store data. Don't do that. This is not tidy, even though, as we'll see later, this is often a convenient way to store data for working with it. This is not tidy because there's multiple observations in more than one row. This is tidy because it satisfies all 3 rules, 1 variable, 1 column, 1 observation per row, and each cell has its own value. And then these are horribly not tidy because we have the year columns spread out across, the year variable spread out across columns, and then we have the data in 2 different data sets, one for cases, one for population. So the moral of the story is always try to work with tidy data, especially if you're, like, say, collecting data in the field. That might not be the easiest way to manually input data, but you know, try to do that when you're collecting data. But a lot of times as a data analyst, you will not receive tidy data. So it's important to understand the structures of a tidy data set and how to get a raw data set into that format. So there's 2 functions that are included in the tidyr package, which comes with the tidyverse, that will help you make your data more tidy. So there's all of the functions I've already talked about and the ones I haven't talked about that will help you as well. But there's 2 in particular that are, I think, really important. And if you're familiar with pivot tables in Excel, this is sort of the same idea. So there's a gather function and a spread function. Now, there are actually newer versions of these functions that are out called pivot longer and pivot wider. So I just want to acknowledge those if you are new to the tidyverse, that these are kind of the newer versions that are designed to make their use a little more intuitive. But I've been using gather and spread for a while. They're described in R for Data Science, the book that I've been using, and they make sense to me, so I like to teach them. But essentially, gather is like you're gathering values across columns and making them into a long data set. And spread is you're taking a long data set and spreading them across columns. So looking at this example, this is table 4A. That was cases by country, 1 column per year. This was not a tidy data set because we have year, which is a variable, spread out across several columns. So in this case, we want to gather that information in a way to make this data set tidy. So I started this exercise with joins because it's important to understand this concept of a key. What is a key and why is it important? You need that to join data sets, but for gathering, the key is another thing to identify. So what is the sort of master variable that defines the values in a data set for what you're trying to gather? So the first thing to do when gathering is to identify what that key is. And so here we have the years. So we can say, okay, in this example, our key value is going to be year. And then the second piece of information is to understand what the value is. And so here the values are the case numbers. So key is year, they're defining what goes in the columns, and then the actual values in the columns and the rows is cases. So this probably isn't making a lot of sense if you've never seen this concept before, but let's just show you what this looks like in practice. So table 4A comes with the tidyverse, so you can just type that into the console. And we're going to use a pipe, so actually, I'm not going to use a pipe, so I'm just going to show you the whole function, just what it does here Table 4A, that's the first argument. Now, there's a couple pieces of information here to be aware of. I talked about the key as the name that you want to call the keys, and then the value is the name you want to call the values. So here we're saying key is year, value is cases. And in this bit, there's 1 to any number of columns you can enter here, which are the set of columns you want to gather into long format. So looking at table 4A, we want to gather these like so. So now it's like a pivot almost, or it is literally a pivot where we're taking these values, putting them into one column and matching them to the corresponding rows for the year they fall under, as well as the country. So now this is tidy, at least for the cases. So hopefully that made sense, what that's doing. Graphically, here's a depiction there. So it's taking literally these columns, making them into long format to make that data set tidy. Now spreading is the other part of this. This is sort of opposite of gathering. So you're taking, in this case, here's table 2. This was our untidy data set where we have keys in one column spread out across multiple rows. So the first 2 rows should be in one row. So we've sort of mixed up 2 keys into one column here, cases and populations. So spread is the, spread is the opposite of gather. So we will copy that. Again, table 2 comes with the tidyverse, so you just type that in. You can see that there. Here, because these columns already exist, we don't need to use quotations here. So we can use them directly into the function itself. So we know that cases and populations are our keys, and these are the values that correspond to each key. So key equals type, count equals value. We spread that, and there we go. Now this is the tidy data set. So now cases and populations are their own columns with the corresponding counts underneath that column name. Each row is an observation. We're good to go. And also for these examples, I didn't save these as objects in my environment. So we can always do that like that and look at them later when we're done. So that is spreading and gathering. Again, conceptually kind of hard to grapple with, but the functions for working with them and tidyr and the tidyverse are very simple. So now we're going to do exercise 7, where we're going to take the fisheries data set and we're going to gather the species columns and make the data untidy. And it'll be clear why we're doing this later. And I should probably do a better job explaining why we're going to make it untidy, but we'll see moving forward why we want to do that. So I'll put 5 minutes on the clock and let you have a go at it, and then we'll talk about the results. All right, that's 5 minutes, and we have 12 minutes technically until lunch. And as always, I want to respect everybody's time. So I will do my best to finish this lesson at 12:30 or very, very shortly thereafter. So um, this is I think a fairly simple, straightforward way to combine the data, and it's actually pretty common with biological data sets where you have different species across different columns. And as we'll talk about in a second with Summaries, it's often easy or useful to gather a data set where species names are in a column. So let's just look at fish stat. So we have bluefish, common snook, mullets, pinfish, red drum, and sand sea trout in columns. So our key is going to be the species. That's what we want to call that new column name. And the value column, we're going to call it count, because we know that these are counts of how many fish were caught at each date and each station. And then the rest of this is just the column names. Again, one to many columns that we could add here that corresponds to all of the columns that we're gathering. So we're taking all of the remaining columns and putting them into two, with one column called species to identify which species you're looking at, and another one called value to identify the counts. So there we go, head, gather dat, and now look at that. It's, again, not tidy because we have a variable within a column, but as I'll show in a second, this can be useful for summarizing data. All right, on the home stretch here before lunch. All right, so group by and summarize is the last thing I want to show you about dplyr. This is a really efficient workflow for summarizing data sets. So hypothetically, just throw it out there, maybe we want to get an average catch of all species or of each species throughout all time, all stations, all dates. We can do this with group by and summarize. So there's two steps to this workflow. There's two functions you want to use. So first off, we need to use group by, which will let us set up a way for R to know what our grouping category is in our data set. So we have our gathered data set, and I've just grouped it by the species column, which we just made. So I'm going to look at the by species data set, which is the one I just made by grouping by. And we'll see that it looks exactly the same as our gathered data set. So very similar, but there's this bit of information at the top here that says now there's a groups attribute associated with this data set. So the species column is now a grouping variable, and there's 6 categories in there that we're grouping by. So we can take the next step, use a pipe, and summarize this data set by species, because that is our grouping variable that has grouped this data set. So we can use summarize, which is a lot like mutate, but it condenses, synthesizes, summarizes the data by that grouping factor. So I'm going to say I want to take average count for all species. So I'm going to call that av count. Again, this is what the new column is going to be named, whatever you want to call it. And I'm going to take mean of count the existing column using the mean function. So I run that, look at the result, and look at that. We have a summarized data set of average count across all of the species through all time and all stations in all Tampa Bay. So pinfish, highest average count. This is really small, kind of bait fishy type thing, so not really surprising that they're all that abundant. Other things, bluefish, these top predators, mullets, even not as abundant. So again, this is, one step, two steps, we can get a summarized data set across all sites and stations. So there's a few more things to say about summarizing, and rather than going through this, I will just show you one final example before we do our last exercise. So you can, first thing to note, so this is multiple summaries. We can use multiple summaries. So here I just took the average. We can use other functions to get different summaries. So we'll get a new column for each function we want to sum, or each summary that we do. And we can use multiple groups. So in this example, I just grouped by species, but maybe I want to group by, I'll look at the data set to make this decision. We'll just group by year, so we can look at trends over time. So year and species are now our grouping variables. So I just ran those first two lines without completing the pipe to show you that same data set, but now year and species are our groups. 126 unique combinations there. And then we could pass that to the summarize function. Here I'm taking just a count, the minimum, the maximum, and the total. Just for fun, I'm going to change that to the mean as before. So more sums, look at that. And now we have a summarized data set where for every year and every unique species combination, we have a count of how many observations were in those rows across the data set. We have what the minimum catch was, maximum catch, and then the average. So super powerful way to summarize data sets here with just two commands, group by, summarize, and then any of a number of functions you want to throw in there to summarize your data set. So there you have it. I will let you play around with group by and summarize as we go into the break. I think I'll put 5 minutes on the clock. I'll let you guys go through this, and then I'll very quickly walk through the results of this exercise, and then we'll break for lunch. So 5 minutes on the clock, and have at it. Oh, and also the gathered data set, the gathered data set that you completed in exercise 7 is going to be the input to this exercise. So if you need to recreate that data set from your script or the live coding script, make sure to run that code again. All right, that's our last exercise for Data Wrangling 2. As I said, I am going to very quickly walk you through hopefully what you just did. So I'm going to go back to my live coding script, and we are going to take GatherDat, which was this that we created in exercise 7. So if you don't have that, you can use the live coding script and recreate that. So I'm going to start with GatherDat and read my own instructions. Let's see, filter the data by gear type 20. And pinfish, yes, species equals pinfish. So we have to filter this way now because the data are in long format. Before, when it was in wide format and tidy, we could just select with the select function the pinfish column. So that is actually one little overhead that you'll have to deal with when you have these data in long format. You have to filter instead of select if you want specific variables. So then we'll group by reference. So that was our site. And then we'll summarize the count to get the average. So call it average count, mean of the count column, and then arrange by av count, or whatever you named that column, ex8. When we'll look at that. So by default, arrange will arrange it in ascending order. A neat little tidbit is if you don't want to do that, you can use the minus to arrange it in descending order. So I just did that for fun. But now we can see which stations have the highest pinfish count across all time in this data set in Old Tampa Bay. So highest average count. So if I wanted to get some pinfish, I'd go to this place. Not advocating that you do that, but as a data scientist, this is probably good context for understanding what's going on with the fish community in this data set. So with that, we are officially on lunch break. So we'll give you guys the chance to step away from your computer, get some food, get some water, go outside, yell at the sky, do whatever you need to do to not think about R in this time in between sessions. But I hope to see you all back here at 1:30 sharp. We will continue on with my favorite part of R, making plots and working with spatial data. So we'll also be here moderating the chat, or I'll be looking at the chat as I eat my lunch. So if you have any questions, feel free to reach out, and have a good lunch. We'll see you at 1:30.